Hey folks, my name is Nathan Johnston, and welcome to Lecture 28 of Introductory Linear Algebra. In today's class, we're going to start looking at something called the span of a set of vectors. And the idea behind spans is they turn any old set of vectors into a subspace, okay? So they turn arbitrary sets of vectors into sets that have those extra two properties, the fact that they're closed under vector addition and closed under scalar multiplication. Okay, so they're going to sort of fix those two gaps in sets that don't satisfy those two properties. Okay, so here's sort of the motivating example. Suppose that we've got a set that contains just the vector 2, 1. Okay, so it's a set in two-dimensional space, and it contains only the single vector here. That's not a subspace of R2. For example, it's not closed under scalar multiplication, right? If I take that vector 2, 1 and multiply it by 2, I get the vector 4, 2, which is not in that set, right? The set only contains 2, 1. Okay, so how would I sort of fix that problem? How would I make that set more like a subspace? Well, one thing that I could do is I could just throw that vector 4, 2 into the set. Okay, I would just sort of patch up that one hole that I just noted. Okay, so if we throw the vector 4, 2 into the set, now we're gonna have the set containing two vectors, 2, 1 and 4, 2. Okay, and now we ask the question again, is that a subspace? Okay, and hopefully you agree, no, that's not a subspace, right? It's still not a subspace because, well, I mean, we didn't have to multiply 2, 1 by 2. We could have multiplied it by 3. If we multiplied by 3, then we would get the vector 6, 3, and that's also not in this set. All right, but we could try, just repeat, okay? Okay, great, here's another vector that should be in the set that's not. Just throw it in there, just put that in the set. Okay, and then you play this game over and over and over again, okay? I mean, there's sort of nothing special about the scalar 3 either. We need all scalar multiples of 2, 1 to be in that set. So, okay, let's just throw all scalar multiples into the set, okay? Let's consider the set all scalar multiples of the vector 2, 1. Well, finally now, we actually do have a subspace. The set of all scalar multiples of the vector 2, 1, that's a subspace, and actually it's what we call the span of the vector 2, 1. All right, so let's ramp this idea up a little bit, okay? So it's definition time. What is the span of an arbitrary set of vectors? Rather than just a set of one vectors, an arbitrary set now, well, it's the same idea, okay? It's what you get if you take that set and sort of patch up all the holes, you know, throw all of its vector additions in there and throw all of its scalar multiples in there as well. Okay, well, another way of phrasing what I just said is you take those vectors and throw all linear combinations of them in there. Okay, and when you do that, you get a subspace. That's the point of doing this. It turns that set that you started with into a subspace. All right, so a little bit more formally here, suppose that you've got a set contains k vectors, and then, well, if you construct the set of all linear combinations of those vectors, we call that the span of that set, or the span of those vectors. And we denote it either by span of B, if B was the name given to the set, or span of, you know, that list of vectors. Okay, and again, the point of this is it turns this set here, which is not a subspace, into a set here that is a subspace. It sort of patches up all those holes. So for example, we would say span of the vector 2, 1. Well, that refers to the line through the origin and the point 2, 1. Okay, it's the line in the direction of that vector 2, 1. It's the line that we just talked about. Okay, the span of the vector 2, 1 is exactly this set that we just constructed up here. Okay, so let's just go through a couple of sort of introductory examples about the span of sets of vectors. Okay, so first example, let's show that the span of the three standard basis vectors in R3, let's show that that is all of R3. Okay, so if you take the vector, remember this E1, that's the vector 1, 0, 0. And the vector E2, that's 0, 1, 0. And E3, that's 0, 0, 1. So the subscript just tells you where the 1 is in the vector. Let's show that the span of those guys is all of R3. And this goes all the way back to something that we did way back in week 1, okay? We talked about how you can write any vector as a linear combination of these standard basis vectors, okay? And we noted that, hey, if you take any vector in three-dimensional space, then that vector is, well, its first coordinate times E1 plus its second coordinate times E2 plus its third coordinate times E3. Okay, so what we've done here is we've shown that any vector in R3 can be written as a linear combination of these three guys. In other words, every single vector in R3 is in the span of those three standard basis vectors. Which is enough. That shows that these two sets are the same, right? Because this set lives in here, and now we've shown that the other inclusion happens as well. Everything that's in the set on the right is in the set on the left. So they're actually the same set. And I mean, the same thing happens in more generality. Like there was nothing special about 3 dimensions here. In n-dimensional space, the span of the n different standard basis vectors, so the n vectors that have a 1 in one spot and zeros everywhere else, the span of those vectors is all of Rn for the exact same reason. You can write down a linear combination like this, except now it'll have n terms instead of just 3. All right, let's go through another example, okay? What is the span of this set of 2 vectors here? What's the span of 1, 0, 3 and minus 1, 1, minus 3, okay? In particular, describe it geometrically. Is it a line? Is it a plane? Is it something else? Well, let's figure it out. Okay, so the way to sort of mathematically phrase this question, we're trying to determine what the span of these 2 vectors is. In other words, we want to characterize the set of vectors of this form. We want to know which vectors x, y, z can be written as a linear combination of these 2 vectors that were just given to us. Which vectors are linear combination of 1, 0, 3 and minus 1, 1, minus 3? In other words, when do there exist a C1 and a C2 such that x, y, z can be written in this form? Okay, and this is a linear system. Okay, you just have to be a little bit careful about, what are the variables in the linear system and what are constants in the linear system. What we're doing is we're thinking of this vector x, y, z as given to us. Okay, and then we're asking, hey, is x, y, z in that span? In other words, do there exist C1 and C2 such that this happens? So C1 and C2, those are the variables that we're trying to solve for in the linear system. All right, well, let's write out the linear system a little bit more explicitly. And the way you do that is you just match up entries in the vectors. So x equals the first entry on the right, so C1 minus C2, x equals C1 minus C2. And then y equals the second entry on the right, so 0 C1 plus C2, which is the equation down here. And then z equals the third entry on the right, so 3C1 minus 3C2, which is the bottom equation down there. All right, so that's the linear system that we want to solve. But again, keep in mind, x, y, z, you're thinking of them as given, they're constants. C1 and C2, those are the variables in the linear system that we're trying to solve for. So when you turn this in to, your sort of augmented matrix form, you get something like this, okay? Where x, y, and z, those are just whatever numbers are on the right-hand side. Those are not variables in the linear system. Instead, the variables C1 and C2, well, remember, columns of your matrix correspond to variables. Okay, so this first column is like our C1 column, and the next column, that's like our C2 column. All right, now let's get that in row echelon form so that we can determine when there's a solution, right? Which vectors can be written in this form? In other words, when does this linear system have a solution? All right, so get in row echelon form, we just need to zero out this entry down here and that one down there. And fortunately, just one row operation does it. If you do row 3 minus 3, row 1, then you're going to get this new bottom row down here. Okay, and then we're asking, when does this linear system have a solution? Okay, well, for that linear system to have a solution, we need this quantity down here in the bottom right corner. That's got to be 0, right? Because otherwise you have 0, 0, non-zero, and that means no solution. Okay, so we need this to be 0 for us to have a solution. We need z to equal 3x. Okay, and that's our answer. That tells us what the span is. This vector x, y, z is in the span if and only if z equals 3x. Okay, and well, we know from previous courses that that's the equation of a plane, right? If you're in 3-dimensional space and you've just got some linear combination of x, y, and z equals a number, that's the equation of a plane. Okay, so the span in this case is a plane, and furthermore, we know what plane it is. It's the plane z minus 3x equals 0. Okay, so we're going to round out this lecture just with a couple of theorems to help us understand the span of a set of vectors a little bit better. Okay, so the first theorem that we're going to look at just justifies what we've been saying all along. Why did we introduce the span of a set of vectors? Well, to turn a set into a subspace. Okay, and all this theorem says, theorem 7.1 here, it says that, yeah, that actually happens. Okay, if you construct the span of any set of vectors, you really do get a subspace of Rn. Okay, so we're not going to prove this. The proof is in the textbook, and it's sort of straightforward by the definition sort of stuff. But, we're going to skip over it for time's sake. Okay, it just justifies our intuition why we introduced this in the first place, because spans give us subspaces. Okay, for example, I mean, like in this previous example right up above here, we showed that the span of these 2 vectors here, well, it's this plane through the origin. Well, planes through the origin, they're subspaces. Okay, so this theorem's just saying something like that always happens, okay? The span of any set of vectors, it's always, either just the set containing just the 0 vector, or a line through the origin, or the plane, or a plane through the origin, or, a higher dimensional thing through the origin that is also long and flat. Okay? All right, next theorem gives us a nice way of constructing a particular subspace that comes up over and over and over again, the range of a matrix, okay? And so what this theorem says is if you ever want to know what the range of a matrix is, well, you can go through the method that we went through in the previous lecture to compute the range of a matrix, but there's an easier way. Okay, and the easier way is to notice that, hey, the range of a matrix is just equal to the span of the columns of that matrix. Okay, and this is really nice because it gives you the range of the matrix without doing any computations whatsoever. Okay, it's just, you write down what that matrix is and then you list out its columns and, oh, the span of that, that's what the range of that matrix is. Okay, and fortunately, this theorem, we can prove it in just a line. It follows almost immediately from something that we did in an earlier lecture. All the way back in week 3, we learned from block matrix multiplication that if you ever take a matrix and multiply it by a column vector x, so you're doing A times x, then what you get is, well, you get a linear combination of the columns of the matrix. Okay, so here A1 is the first column of A, A2 is the second column of A, and so on. AN is the last column of A. And you just get a linear combination of those columns where the coefficients in the linear combination are exactly the entries of the vector x. Okay, so what this tells us is that outputs of A, right, vectors of the form AX, in other words, members of the range of A, those are exactly equal to linear combinations of the columns of A. In other words, members of the span of the columns of A. Okay, right here, range of A, well, its members look like this, AX. Span of the columns, its members look like this. Okay, and as you range over all possible values of the vector x, you get that, hey, this set has to equal this set because all of these equal all of these. Okay, so that's all there is to the proof of that one. Okay, so for example, if we return to a 2 by 3 matrix that we looked at in the previous lecture video, this matrix over here, 3, 1, minus 4, 6, 2, minus 8, well, we see immediately what the range of this matrix is. The range is just the span of these 3 columns. It's the span of 3, 6, and 1, 2, and minus 4, minus 8. Okay, so in a sense, that's a fine answer. Certainly it's a correct answer, but there's a simpler and better final answer as well. We can simplify this a little bit because, hey, notice that 3, 6, that's a multiple of 1, 2. Okay, so 3, 6 is itself a linear combination of 1, 2. And similarly with minus 4, minus 8. Minus 4, minus 8, that's a scalar multiple of 1, 2. Okay, so it doesn't actually contribute anything to the span, right? If something can be written as a linear combination of these 3 vectors, well, then you could also write it as just a linear combination of this one vector in the middle. You could write it as just a linear combination or a scalar multiple of the vector 1, 2. Okay, so in other words, the range of this matrix here, in this special case, it's just the span of this single vector as well. You can forget about the other columns. They don't actually contribute anything to the span. I mean, equivalently, we could have said, oh, this is equal to the span of just 3, 6. Or also, it's equivalent to the span of just minus 4, minus 8. I just picked 1, 2 because it's sort of the simplest of those 3 vectors, so why not choose that? Okay, if we go back up to our answer from the previous lecture, just to compare with the answer that we got there when we computed the range sort of directly from the definition, so that's what we did here, right? We found that the range of this matrix was the set of all multiples of this vector 1, 2. So it's the same answer, right? The set of all scalar multiples of 1, 2, that's the span of that vector 1, 2. Okay, so we found the same answer, just sort of a bit more long-winded way to get it. All right, and then the final theorem that we're going to look at in today's lecture shows that there's a nice connection between spans and invertibility of a matrix. Okay, so we've already seen sort of one characterization of invertible matrices. We saw that a matrix is invertible if and only if its reduced row echelon form is the identity matrix. If and only if it can be written as a product of elementary matrices. If and only if linear systems with that coefficient matrix have solutions, and so on. Like there's like a list of 6 equivalent conditions that were things that were equivalent to invertibility. Well, now we've got even more things that are equivalent to invertibility, all right? So theorem time, even more characterizations of invertibility. A is invertible if and only if the range of that matrix is all of Rn. In other words, if and only if when you multiply that matrix, you can get any possible output. Okay, you don't get a sort of a strict subspace of Rn, you just get the whole output space as the range of that matrix. That's equivalent to invertibility. Okay, that's also equivalent to the columns of that matrix spanning all of Rn. In other words, if you take the span of A1, A2 up to An, those columns, then you get all of Rn. You don't get a strict subspace, you just get the whole space Rn. Okay, and that's also equivalent to the same thing happening with the rows of A. Okay, if the n different rows of A, if you take their span and you get all of Rn, that matrix is invertible. If you get sort of a strict subspace of Rn, something smaller, then it's not invertible. All right. Even though there's a lot going on in this theorem, fortunately, it follows almost immediately from things that we've already proved earlier in this course. It just follows immediately from earlier theorems. So first, we're going to show that properties A and C, those are equivalent to each other. All right. So the way that we see this is we combine two theorems. Okay. So we're going to combine a theorem from week 6 and a theorem from week 3. Okay. So the theorem from week 6 says that A is invertible if and only if the linear system ax equals b always has a solution, no matter what the right-hand side here is. Okay, so that was our first characterization of invertible matrices. Okay, and then the theorem from week 3 is the one that we just used up above on this page. It said that A times x, that's always a linear combination of the columns of A. Okay, well, if you stitch these two results together, what that says is that A is invertible if and only if ax is a linear combination of A's columns, so A is invertible if and only if a linear combination of A's columns equals B always has a solution for all B. Okay, in other words, the columns of A have to span all of Rn. No matter what vector from Rn I pick, I can always find some way of writing it as a linear combination of A's columns. Okay, in other words, it's always in the span of A's columns. All right, so you just stitch those two theorems together, you get equivalence of A and C almost immediately. Okay. The equivalence of properties C and D, so properties C and D are that the columns of A span all of Rn versus the rows of A spanning all of Rn. Well, the equivalence there, that just comes immediately sort of from stitching together what we just wrote, and the fact that a matrix is invertible if and only if its transpose is invertible. Okay, so this is also one of the first things that we proved about invertibility of matrices. A matrix is invertible if and only if its transpose is invertible. So, I mean, we just proved that A and C are equivalent to each other. Well, now I know that A is, like this property A here, that's equivalent to A transpose being invertible, and that just swaps the roles of rows and columns. All right, so that gives me that, yeah, these two are also equivalent to each other, okay? A is invertible if and only if A transpose is invertible, if and only if the columns of A transpose span all of Rn, if and only if the rows of A span all of Rn, okay? So it's just because transpose swaps rows and columns, and we already know something about the columns. All right, and then the last one, we're going to show that properties B and C are equivalent to each other, okay? So we're going to show that the range equaling all of Rn, that's the same as the columns of A spanning all of Rn, and this follows just immediately from our previous theorem, theorem 7.2. Okay, the range is the span of the columns. Okay, so if one of them equals all of Rn, then the other one has to equal all of Rn as well. Okay, so this is just theorem 7.2, the theorem back one page. Okay, it's just, I mean, this set here, range of A, that is equal to the span of the columns. So one of them equals Rn if and only if the other one equals Rn. Okay, so that does it for the proof. I just want to make one final geometric note about something that's really nice about this theorem. It tells us something really nice about invertibility of matrices, sort of a geometric interpretation of invertibility of matrices. And it comes from looking at properties A and B here. Look at that equivalence. A matrix A is invertible if and only if the range of that matrix is the entire output space, the entire n-dimensional output space, all of Rn. Okay, so the way geometrically to think about this is a matrix is invertible if and only if it doesn't squish space at all. It sends n-dimensional space to n-dimensional space rather than squishing it down to a lower dimensional space. Okay, it doesn't squish it down to some n-1 dimensional or smaller subspace. Okay, because, well, I mean, if it did squish space down like that, then it wouldn't be invertible because you can't undo a squishing like that. Like, when you squish a higher dimensional space into a smaller dimensional space, you throw away information, and there's no way to undo that throwing away of information. Okay, and this relates back to a picture that we've seen earlier. When we first introduced invertibility of matrices, we noted that projection matrices are not invertible. Okay, and the way to think about that geometrically is, like, there are different vectors that get mapped to the same spot. They get projected down onto the same spot on the line. Okay, so if I asked you, okay, invert that, undo that action there, I mean, you can't, because if I give you just this vector here, if I give you just A times V, you can't tell me, did it come from V or did it come from W? You can't undo that squishing. Here in this matrix here, the matrix A that does this projection down onto the line, you're squishing all of two-dimensional space down onto a line, onto one-dimensional space. And there's sort of no way to pull that line back apart to get all of two-dimensional space. So you can't undo that. You can't invert that matrix. All right, so that's exactly what the equivalence of properties A and B in that previous theorem are saying. They're saying the matrix A is invertible if and only if it sends n-dimensional space to n-dimensional space. Nothing gets sort of lost, projected down, or anything like that. Alrighty, so that's enough for today. I will see you next class.